Hello everyone, again welcome to this NPTEL course on Advanced Pre-Stressed Concrete Design. We are in module 4. In this lecture, this is the fourth part of this module. Here we are going to talk about multiple things, which includes what is a pressure line, how to find the location of a pressure line, crack widths, deflection, and stress analysis of a flexural member. All these things that we will try to cover in this part 4 of this module 4. Well, expected learning outcomes are the student should be able to explain what is the Kern point and how cracking moment can be calculated, and student should be able to explain the concept of pressure line and its effect on pre-stressed member design, and one should also be able to estimate camber and deflection in pre-stressed concrete members. So, these are the things which we will try to learn in this part of the lecture. Okay. So, Kern point, some of you might have learned the design when you do the foundation design, there is a Kern zone, right. Similar to that, here in pre-stressed concrete sections also, we try to see that when the resultant compression is within the specific zone of a section, the tensile stresses are not generated. This zone is called the Kern zone of a section. Now, again, we looked at three concepts of analysis, right. So, we studied stress concept, right. The second one is the force concept, and the third one is the equivalent load concept. In that, we said in pre-stress system, the most common one in design that what would be used is the force concept or the C line concept, C method, right. So, the system is going to be assumed to be in elastic state, that means no crack, and depending upon the location of your compression force, we just apply this compression force as an external force and then we do the analysis that we have discussed it in the previous chapter. Now, what is the maximum zone within which this compression force can move is called as Kern zone, for no tension stresses should be generated. Okay. Now, for a section that is symmetric about vertical axis, we know that the Kern points lie on the same distances from the CGC, right. So, for example, if you look at this rectangular section and if you say the CGC is this, you will find that the top Kern zone point and bottom Kern point zone will be same. For a symmetrical cross section, now the Kern zone is going to be this highlighted area, right. So, that means within the zone, if C is acting, then no tension stresses will be generated. Again, if you remember, if you take this cross section like this, let's say this is your, let's say I take a section. So, this is CGC, let's say this is CGS, and what we are saying is we are going to apply the C. See, this tension force location remains same. Initially, when there is no load acting, C will be here in line with T, but then the C will start moving up as the loads are increased. So, what we are saying is the C, if it is within this Kern zone, then no tension stresses will be generated. So, we have to do the analysis, okay, so that we will see by what is the maximum allowable distance for C to move away from T that we have discussed. Now, for example, if you look at this I section or an unsymmetrical cross sections, you will find that this zone, which is KB here and this is KT, will be different. So, KT will not be equal to KB, whichever is the region that you will have higher area, that, for example, here the top flange is having more area than the bottom flange. So, KT is expected to be higher than KB, right. So, this is for symmetrical cross section and this is for an unsymmetrical cross section. Okay. This we have already discussed it in the previous parts of the module, but just for clarity, again we are putting what are the difference between how the internal forces are there between a reinforced concrete section and a pre-stress section. We have seen that in case of pre-stress concrete section, if load is, let us say, W, and this is the way the lever arm is there, Z1, and the internal forces are C1 and T1, and we always know that C1 will be equal to T1, okay, which are compression and tension forces are transferred due to self-weight, and let us say this is C2 and T2 are compression and tension forces under service loads. So, under self-weight, of course, C1 and T1 will be lesser than C2 and T2. Now, how do we get the resistance? When W2 becomes more than W1, and you will find that C2 has to be greater than C1 and Z2 will be approximately equal to Z1 in this case. Okay, this is for a reinforced concrete, right, for a reinforced concrete. So, here you find that the lever arm does not change in a reinforced concrete, but I get moment resistance by increment in your internal forces. That means compression and tension forces increases. But we have seen that in a pre-stress concrete member it is exactly opposite. The internal forces does not change much, but the moment resistance I get by the movement of these internal forces. Okay. So, when RC members are subjected to increased external load and flexure, the values of compression and tension in the steel increase with increasing external load. However, the lever arm does not change, only the internal forces changes, that we have studied it. The lever arm remains nearly constant as the external load increases. But if you go to pre-stress concrete member, we have seen that again two cases. You see here, this we are looking at a transfer due to self-weight, and this is under service load C2 and T2. So, two conditions, W1 is at, let us say, transfer, W2 is at service load. Now, if you look at the internal forces C1 and T1 again, C2 and T2 again. Now, we will find that the internal forces will be nearly same. Now, again why? Because already we have stretched the cable to a high tension force, right, and up to 75% of a characteristic stress. So, under service loads, that increment in force is not going to be that significant, right. So, then how do I get the moment resistance? So, moment resistance is always C times lever arm, or which is equal to T times lever arm. If C and T does not changes, then only way I can generate moment resistance is by increase in your lever arm. That means the compression force will start moving away from tension force, right. So, that is the concept in pre-stress concrete. Under service conditions, when the crack widths are very minor and the system, the pre-stressing steel is not yielded. Once the pre-stressing steel yields, then this assumption is not valid, right. Okay. So, in pre-stress member, as we have discussed, a transfer of pre-stress C and T are located very close to each other. Let us say if W1 is 0, then C1 will be at the location of when W1 equal to 0, when there is no external load. Now that we have some external load, now C is going to move up, and that movement is nothing but your delta Z, let us say, or in other words Z, that is basically going to be your lever arm, that should be proportional to the externally applied moment in that particular cross section. So, as the external loads are increasing, the C will gradually shift upward, which is significantly increases the lever arm between the compression and tension forces. So, by only change in the lever arm in pre-stressed systems under service loads, when they are not cracked or maybe slightly cracked, you get this kind of behavior. Okay. Now, Kern point. So, what is the lower Kern point? So, now that we have seen what is the relevance of force method of analysis, we are going to analyze the cross section only in terms of C by finding out where the location of C is. So, for finding the lower Kern point, we have to see when C is at a transfer of pre-stress is located at the bottom Kern point, then the stress in the upper edge will be 0, right. So, typically the values of upper and lower Kern points are denoted as KT and KB respectively. So, let us see now what is this. For example, you see here this is CGC of the cross section and this is the location C. So, in force method of analysis, again you can look at the videos of the force method of analysis. We are going to analyze this friction as though like C is acting as an external force, because T is always going to be constant and C is also going to be constant, only C is going to move away from your tension force. So, we put this C as an external force at a distance KB at transfer, and we are trying to find out what is this KB. So, that is what we are trying to find out, but we know that when C is acting, I should have the stress at the top should be 0. Okay. So, when C is acting at a distance KB, the stress at the top has to be 0. So, this would be the resultant stress profile when the compression is at the lower point. So, using this condition of stress at the top to be 0, now I can find out what is my lower Kern point. So, now how do we do that? We know that. So, these are the nomenclature. C is your compressive force at transfer, KB is the bottom Kern point, YT is the topmost fiber distance, and sign convention as usual, compression we take it as negative and tension we take it as positive. Right, now let us see how do we calculate. So, we have seen that the stress at the top fiber is 0 and only C is acting. So, compression concentric component minus C by A is the stress. Now, there is a moment, C into KB is the moment, and now we are calculating the stress at a distance of YT at the top fiber. So, but why here we have taken plus? So, here you see because this is tension, because C is acting below the neutral axis, at the top it will create tension. So, this we are equating it to 0, then I can find an expression for KB as R square by YT. Now, how did I get R square by YT? Now, the moment of inertia we know that I is nothing but A into R square. From your basic strength of materials you know that. So, I can be written as A R square, and then if you solve for it, KB will become R square by YT. Okay, where R is your radius of gyration and KB is your bottom Kern point and YT is the topmost fiber distance. Right. Now, how do we get the upper Kern point? Same concept. Now, as you have seen, upper Kern point is above the CGC, and what is the distance at which maximum C can act, so that the stress at the bottom fiber will be 0. Now, when the C at transfer of pieces of point, the stress at the lower edge will be 0. The levels of upper and Kern points from CGC are denoted as KT and KB respectively. Now, let us look at it. Now, the C has now acting at a distance KT above CGC, and the condition is at this location the stress has to be again 0. So, we do the same exercise. Now, here C is a compressive force at transfer, YB is the bottommost compression and tension, right. So, if you substitute stress at the bottom fiber equal to 0, there is going to be a concentric stress component C by A. Now, the moment due to this is going to be C into KT, which is acting at the top. Again, because it is acting at the top and I am calculating the stress at bottom, this is going to be positive because it is going to create tension, right. So, moment by I times the distance of the fiber, which is Y, is 0. So, if you equate that again, I can be equated as again same A R square. Then if you substitute that, you will find that the lower Kern point or the upper Kern point will be R square by YB. So, again these are the nomenclature. KT will be a top Kern point, YB is the bottommost fiber distance, and R is your radius of gyration. So, now we have defined what is lower Kern point and upper Kern point. It is just like your moment of inertia or your radius of gyration, it is a sectional property. The moment you are given with your sectional property, you can find your upper Kern point and lower Kern point. Now, let us see what is the pressure line, because these are all the concepts useful for when you design the cross section and member in terms of what should be the pre-stressing force, what should be the level of your eccentricity. So, it becomes very important to understand what is the pressure line, what is the lower Kern point, what is upper Kern point. Now, let us see what is the pressure line. So, pressure line in a beam can be defined as the locus of resultant compression force along the length of the beam. It is also called as thrust line. So, for a particular load, if you try to find out along the length of the beam where the locations of this compression force is. So, that is called as pressure line. So, now why should we calculate this pressure line? It is typically used to check whether the compression force either at transfer or service loads is falling within the Kern zone. So, if C is within the Kern zone, then we know that that particular section will have tension stress or not. So, that is the idea, right. Now, the eccentricity of the pressure line from the CGC should be less than Kb or Kt to ensure that the C should be within the Kern zone. So, that means EC is the location of your compression force from the CGC. So, just like we have eccentricity of the cable profile, now I can also define the eccentricity of the pressure line, which is your EC. That should be always less than Kb or Kt. Then only we can say that the C is going to be within the Kern zone for a type 1 member. So, now we have again three types of designs: type 1, type 2 and then type 3. In type 1, the stress can never go to tension. Type 2 and type 3 stresses can become tension, but there are sort of limits for it, right. So, these are the three types of members that we design for flexure. Type 1, absolutely there are no tension stresses allowed, but type 2 and type 3 we allow tension stresses, but there are limits for it. Okay. So, if you look at it, this is what you have. The moment I choose my cross section dimension, so I can see that this is your lower Kern point. What you see here is the lower Kern point, dotted points, and then similarly this is the upper Kern point, that what you see here, right. And this is your CGC that we know, and the red color line is nothing but your CGS. This is your red color line. Now, this light blue color is basically the location of your compression force. For any demand on this cross section, we know that the C has to move away from T. How much it has moved away from T gives you an idea of what is the pressure line, right. This is the pressure line at transfer. So, you can see that the pressure line is very close to that of pre-stressing stand at support location, because there is no external moment at this section. That is why pressure line and CGS will coincide. Pressure line EC will be equal to E. But however, if you go to the mid span, you see that the EC or the pressure line has moved away from the red color line, which is your CGS. This is the tendon line. Okay, this is the tendon location, pre-stressing tendon location, and this is your pressure line is nothing but your location of your compression force C. Okay, so that's what we are calling this light blue color line. Now, how to find this location of your compression force? We have seen that at any cross section, always C will be equal to T, and we have seen that the C and T in pre-stressed concrete, C does not change, right. That is an assumption that we are making. So, that means for any given moment, I can say that it will be C into lever arm will give me the moment. If I need lever arm, then I can directly write that it is equal to M by C. So, that is what we have here. And now that you got the lever arm, and lever arm will always be equal to E plus EC. If I know the lever arm, and typically the E is given to you, E will be given. E will be given to you. Typically it is a given. So, I can quickly calculate my EC once I know my Z, right. To get Z, of course, I need to know what is the moment that is acting in this cross section. At transfer, M is always the moment due to self weight, and EC is nothing but your eccentricity of your pressure line. Okay. Now, at service stage, this is a transfer. Now, what is the difference between transfer and service? At transfer, only self weight will be acting, and there are not going to be much loss, but in service, again there will be drop in pre-stress also. We have studied that in the losses section. So, we have to calculate that. Okay, so this we have seen and service stage. So, let us look at it now. So, you see here the previous case the pressure line was calculated from the moment due to self weight, we did that. Okay. And as you can see, pressure line for a simply supported beam gets shifted from CGS with increasing moment towards the center of the span. But now, when the service loads are also acting, right, now you will find that more moments are acting in the cross section. That means more the C will move away from your CGS. Again, the CGS is this, right, red color line. Okay, and you see here now C was originally here at this location. Now it has gone and acting like this, right. So it has moved by this much distance in this cross section. That is your lever arm, right. So that lever arm again can be calculated using this. Okay. So now this, how do you calculate this lever arm? Lever arm is nothing but moment service that is acting in the cross section divided by the compression force. Once I know the lever arm, now EC is nothing but Z minus the eccentricity of the cube, right. So I can find the location of the eccentricity of the compression force, right. And again we see that for type 1 member, tension is not allowed under service condition, that we have discussed that. If tension is not allowed at transfer, C will always lie within the Kern zone. For no tension top and bottom, the magnitude of VC should be less than kVnt. So this is also, I mean, not really only at transfer, this is at service also. Okay. Right.